Let me start. It's going to be a bit of a different talk than the talks that you have heard so far, because I'm not going to show you a very recent advance with very mathematical tight bounds. What I'm going to try to show you is how statistical physics and statistical inference can come together and provide a very fertile point of view on how to analyze many of the problems that we always discuss when we talk about training multi-layer neural networks. And let me start with this notion of causality, which is a notion that it's implicit in all the work that we do. I think that we look for causality and we look for explanatory models because we have evolved in a world with laws of physics in which causality is the norm. So in the world, there is a dynamics and causality. So events X result in events Y. So there is a link from X to Y, where X could be a function of time and Y could be a function of time. And we think that X causes Y, or X is one of the components, one of the causes that results in Y. Now we are in this world and we have a brain, and our brain is going to be this purple box with parameters W, so as a neural network is. And then when we see an input X in the world, the X would like to result in Y, but X is an input to our brain and causes an action. And as a consequence of our action, the output is actually a Y prime, which is not exactly identical to Y. And the difference between Y prime and Y reflects our intervention in the process. But the most important thing of this point of view, both with human intervention or without, is this idea of X into Y mappings, which we use all the time when we talk about multi-layer networks. We think of input-output maps, and if we think of a function A that maps an input X, it would be n-dimensional, into an input Y, which would be r-dimensional, so that Y is a function of X. And in the particular case of a neural network or any kind of inference system, the function that maps X into Y is actually constrained by parameters W, is actually specified by parameters W. So again, I use this purple box with parameters W, and I'm going to say that the function that allows me to map X into Y is a function f sub W. And the question that we talk about when we talk about learning is that we don't know these parameters W. We could initialize them, but we would want to learn the proper values of these parameters W. And the information that will allow us to learn comes from a training set. The training set comes in the form of data. Every data point X mu is actually an XY pair. I use a supra-index mu to label the examples. I'm going to talk about having M examples in the training set. And these M examples, each one of them being an input-output pair, is an example of the desired map. So we use this information containing examples to train a neural network. And how do we do that? Well, we say, in actuality, in the real world, X is mapped into Y. But our neural network that has parameters W maps X not onto Y, but into f sub W of X. So what we need is a notion of distance in output space. That's all we need. So that we can say that the error that network W makes on this particular XY example, on this particular pair, is the distance between the output we desired, which is Y, and the output that the network gives us, which is sub W of X. One example of this is the quadratic laws that we use all the time. Is 1/2 of Y minus f sub W of X squared. But it doesn't have to be these quadratic laws. It could be any notion of distance in output space. In particular, actually, if I'm going to try to be a bit more precise, it doesn't even have to be a distance. It doesn't have to be symmetric. The distance between Y and FW of X doesn't have to be equal to the distance between FW of X and Y. It doesn't have to obey triangular inequality. The only property it does have to obey is that distance is always larger or equal than 0, and it's equal to 0 if and only if Y is equal to FW of X. So this is why we can use all these entropic distances and L1 distances, LP distances. So it's a very kind of weak requirement of this notion of distance in output space that allows us to define a loss function. So given a training set, we have these m examples. Each example is, as I said, an xy pair labeled by this index mu. Mu goes from 1 to m. We construct a cost function. And this cost function is simply the average error over the training set. So in every point in this W space, which is a very high dimensional space where every axis corresponds to one of the parameters that specifies the network, we define a landscape over W space. And this landscape is our error function, the learning error, EL of W, which is the error that network W makes on example mu, sum from mu equals 1 to m, and divided by m, if I'm going to think of it as an average. So most learning algorithms are based on an optimization problem, which is finding special values of these parameters W, which we can call W star, that minimizes learning error. And typically what we do is we look for it by using gradient descent, but we heard some beautiful talks yesterday and today about how we can go beyond that and be a little bit smarter than that in how we find the parameters W star. But at this point, essentially, with just a training set and a notion of distance in output space, we have mapped our learning problem into an optimization problem. So I'm just saying things that you all know. I'm just trying to formalize it a little bit. And this optimization problem is complicated. I mean, you are used to seeing very fancy looking landscapes for multi-layer networks, deep networks. But consider a very simple network in which X maps into Y via a parameter W1, and there is a bias W0, so that Y is just some nonlinear function, some sigmoidal function of a linear combination of X, W1X plus W0. It's a very simple example. The parameter space is two-dimensional. I have the bias W0 on this axis and the weight W1 on this axis. And yet I can construct a training set for this function, which is a learnable function, such that the error function in this very simple two-dimensional space is very, very complicated. So we are all familiar with the intuition that when we look at very high dimensional thousands and millions of parameters in a deep multi-layer network, then this surface in which we're trying to solve the optimization problem is a very complicated surface. But still, what we do is try to use simple ideas to try to solve this problem. So let's stay for a moment in this very simple case where Y is a nonlinear function of a linear combination of an n-dimensional input variable X. So I'm mapping n-dimensional inputs X sub I, where X sub I are the components of an n-dimensional vector X in a single scalar U. So I can add a W0 as a very simple extension from n to n plus 1 if I add an x0, which is always equal to 1, so that I can write Y as G acting on the scalar product between an n plus 1 dimensional vector W and the n plus 1 dimensional X. So even in this very simple case, no hidden layers, I'm just mapping input, n-dimensional input into one output. Even in this very simple case, we can implement interesting functions. And let's assume again that we are in a situation of learning from examples. We have the examples xi mu. Each example is an xy pair, mu labels from 1 to m. What is the error that a given network with parameters W makes on the muth example? Well, that error is 1/2 of Y0, Y mu, which is the value that I wanted to get, minus G of the value that I really get, which is G acting on the linear combination of Wi xi in example mu squared. In this very simple case, of course, we can take the gradient. We can actually, I put a 1/2 here so I don't have to carry these factors of 2. I get the argument of the quadratic error, the target Y minus the Y that the network gives me. I get the minus sign. I get the G prime of the linear combination between the W's and the X's. And when I take the gradient with respect to a given Wi, a given component of the weight vector, I get Xi mu. So we know that this can be written in a very simple way if we just keep xi mu and we define everything else as delta mu. So if we define delta mu this way, then the change that we want to make in the weight, in the ith component of the weight vector, in the weight wi, which is going to be minus a learning step times the gradient, the derivative of the cost function with respect to wi, can be simply written as delta x. So our change in the weight, in the ith component of the weight vector due to example mu is simply the product of the input to the unit, the activity xi mu of the input unit times a delta mu, which is an error associated with the output unit. So it's a synaptic rule which only involves the presynaptic neuron or the presynaptic unit I and the postsynaptic unit, which is the output unit on which we compute this delta. And this rule, of course, was known even before we started doing multi-layer networks for this very simple one-layer structure, and it's called the delta rule. So this is the delta rule that we, of course, extend by using backpropagation, by learning how to compute deltas all through the network, not just at the output level. So this is what we always do. You all know that. So now I want to give you a completely different perspective of learning, which is an ensemble perspective of learning, which is a little bit equivalent to the idea of having a bag of hypotheses. So this is my W space. It's a very high dimensional space. Every axis in the W space corresponds to one of the parameters whose value I need to establish in order to train the network. So let's start with a prior, which I call rho 0 of W, which is properly normalized. The integral of rho 0 of W over W gives me 1. And I could pick any network within this ensemble of networks according to its prior probability rho 0 of W. That's a prior. No examples have been seen so far. So I could think of picking a network within this ensemble as making an hypothesis about what is the XY functionality in the real world. The real world is what produces examples, and is an oracle or a real world that sends me examples. So I have these examples x mu, which are of the form x mu, y mu. That's my training set. And let's say one of those examples, and I'm going to define a masking function over this configuration space. And I'm going to say my masking function on a given point W, given that training example takes a value of 1, if the training example is satisfied by that particular configuration of parameters W. That is to say, if the function fw implemented by that point W in W space applied to x mu gives me the correct y mu. So in that case, the network stays in the ensemble. However, if this condition is not met, that is to say, if f sub w acting on the input x mu does not give me y mu, then I am going to eliminate that with my masking function. You can think of this masking function as an indicator function, which essentially is a survival probability. Only the networks that satisfy the condition imposed by the muth example are going to survive this pruning of networks. So essentially what we do is we started with this W0, with this W space in which there was a rho 0 of W, sorry about that. And then after the first example comes in, rho 0 of W is multiplied by this masking function, theta W of xi1. So let's say that all these guys are eliminated because they violated the condition imposed by the first example. So I'm left with the rest. But now the second example comes in xi2, and then this gets multiplied by the masking function theta W xi2. So after I have seen n examples of the training set, I have to cumulatively iterate this multiplicative process. And what I'm left with is an integral over W of rho 0 of W times the product of theta W psi mu multiplied from mu equals 1 to n. So if I started with a zeta 0 with a volume that I had defined to be equal to 1, because I defined the integral of rho 0 of W dW to be equal to 1, it's clear that this masking process will monotonically shrink my availability of hypotheses, will monotonically shrink the volume of hypotheses, the volume of configuration space that has survived the interaction with m examples. So I have this monotonic contraction of the volume of configuration space as more and more examples are introduce. And I always write larger or equal, so C0 is larger or equal than C1, Cm minus 1 larger or equal than Cm, because it's possible that the nth example eliminates a region that has already been eliminated, and therefore introducing a new example does not cause any additional shrinking of the available volume of configuration space, the available volume of hypotheses that survive having been confronted with the training set. So you could think of this W space as a set of original beliefs, as a set of original hypotheses, a bag of hypotheses about how the world works, how is X functionally related to Y in the world that you're trying to model. And what you're doing here is every time you see an example, you eliminate all the hypotheses that are inconsistent with that example. So that's something that, it would be very useful if all of us did as scientists and as citizens, that when a piece of reality tells us, oh, what you believe was incorrect, if we will be able to discard that belief and stay with the ones that are consistent with the data. But it doesn't always happen that way. Anyway, so what I have shown you so far is a very strict form of learning. It's a type of learning where I require perfect matching. I require perfect answers from the networks in order to keep them in the ensemble, to keep them as part of the configuration space. Of course, we want to be a little bit softer than that. We want to allow for the fact that maybe the data was noisy, and we want to make some allowance for not giving the perfect answer. So let's consider again what was the error that the network W made on example mu. It was the distance between Y mu, which is the desired output, and SW acting of X mu, which is the output produced by that particular network. Of course, if FW of X mu is equal to Y mu, if these two arguments are equal to each other, the distance will be 0 and the error will be 0. And then we say the error of W on X mu is 0, and we want the function theta of W for that particular example X mu to be 1. So that where we were before. But what are we going to do if FW of X mu is not exactly equal to Y mu? We want to then incorporate, in some sense, a measure of the error. We want to incorporate what should be this penalty paid, which is not exactly setting the survival probability equal to 0, not setting the masking function equal to 0, but we want to introduce a survival probability theta of mu of W and X mu, which is going to be an exponential function of this error. So when the error is 0, this is equal to 1. When the error increases, this decreases monotonically as the error increases. So you would think that this is a very ad hoc way of proposing what the masking function should be. And actually it isn't. I'll show you later that there is a condition that allows me to derive this form. There is a condition that allows me to decide that this form is the correct form. But I will show you first that this is a useful form. And by the way, when I show you why it has to be this form, I will also show you that beta has to be positive. So what we have done is replaced hard masking by soft masking. Let's say that this is a cut across W space. So we started with the density given by rho 0 of W. The first example came in and it eliminated all the W's that were inconsistent with that example. The second example came in, it eliminated all the W's that were inconsistent with that example, and I'm only left with a region that is compatible with both Psi1 and Psi2. When I introduce soft masking, I'm not completely eliminating those W's. I am decreasing their contribution to the ensemble. These configurations are attenuated away from rho 0 of W, which was their initial weight, by a factor which is exponentially controlled by the error made on the data. So if Psi1 controls this region, then this is attenuated according to the error that this region makes on example Psi1, and this region is attenuated according to the error that the W's in this region make on example Psi2. So now again, we have a multiplicative effect of a soft masking function. So we go from rho 0 of W to rho 0 of W times e to the minus beta, the error that network W makes on psi1. And now this gets multiplied by the exponential of e to the minus beta, the error that W makes on psi2. And I get a factor like that for each example. So now after I have seen the m examples in my training set, I have what survives, what is the volume of the hypothesis that survived, is an integral over W of rho 0 of W e to the minus beta e W psi mu multiplied by mu equals to m. But of course, we know that the product of exponentials is nothing but a sum of the exponents. So I can write this as Cm equals integral over W of rho 0 of W e to the minus m beta E sub L. And I have a factor of m because remember that I have defined the learning error as an average with the 1 over the m factor. So this is the useful part of having chosen this exponential masking, which is that the product of exponentials gives me the exponential of the sum, and the sum is the learning error. So now what I have is an ensemble of networks that all of them started being possible with probability rho 0 of W, and now they are all attenuated by a factor which is e to the minus m, where m is the number of examples, beta, which is my tolerance to error, and the learning error on W. So this is a way to induce a new density, a new probability density over W space away from rho 0. So when we started, we have an ensemble of all possible networks, all possible models, and it was described by this prior density rho 0 of W. So now, after I have seen m examples in the training set, I have trained an ensemble of trained networks, and this ensemble is described by a probability rho m of W, which is rho 0 of W e to the minus beta EL of W divided by Cm, where Cm is just the integral of over W of rho 0 of W e to the minus beta m EL of W. So the integral of dW rho m of W is again equal to 1. So the partition function that I have here in the denominator is simply providing a normalization constant. And note that I didn't have anything, I didn't have to invoke any kind of algorithm for exploring W space. I have moved away of the problem of how am I going to minimize EL sub W? How am I going to solve that optimization problem? I'm saying giving a landscape E sub L of W defined over W space, this is going to be the correct way of defining the trained ensemble as opposed to defining the prior ensemble, which is the ensemble of randomly connected networks according to the probability distribution rho 0. So this I'm going to show you is very similar to some of the things that Francis Bach was telling you yesterday. But before I do that, let me move a little bit further. So I have used my training data. Every point psi xy was drawn from a probability distribution, which is the joint probability distribution. I call it P tilde. The tilde means real world distribution of xy, which is a P of y given x times a P tilde of y given x times a P tilde of x. The P tilde of x describes the region of interest in input space, and the P tilde of y given x describes the functional dependence that we are really interested in. So now, how do we, this partition function that we have defined, Cm, which is dW rho 0 of W e to the minus beta times m times the learning error, is of course depending on the specific set of data points. So even if we fixed m, it depends on which are the m points that we have drawn at random to use as training set. So we assume that these points are all drawn from a probability P tilde of psi. And what we will do is we will take the free energy, which is the logarithm of this partition function divided by beta with a minus sign. And this free energy is going to be averaged over all the possible ways in which we could derive a training set of size m out of sampling the P tilde of psi. So this logarithm of the partition function is a very interesting object, and this is where you'll see the connection with the things that Francis was doing yesterday. This logarithm of the partition function, which because I'm a physicist, I call it free energy, is actually very interesting quantity because you can very easily convince yourselves that a derivative with respect to beta of this logarithm of the partition function, if I take a derivative with respect to beta, it will give me a minus sign and it will give me this sum. But this sum is nothing but the learning error. So now if I knew the free energy, if I knew the logarithm of this partition function, a simple derivative with respect to beta appropriately normalized by m with a corresponding minus sign will give me the learning error. So the learning error is a very important quantity. We always want to know how the learning error varies as we change regularizers, as we change the number of examples in the training set, as we change beta, which is our tolerance of error. But so let's push this a little bit further. So we have a learning error. So again, because I am a physicist, I know that if I have a free energy and a learning error, which is playing the role of the energy, I can compute the entropy. And if I do the algebra for this, it's very, very interesting because the entropy of the process is a Kullback-Leibler distance. The entropy of the learning process is a Kullback-Leibler distance between rho m and rho 0. So is the distance between the posterior rho m of w and the prior rho 0 of w. So the prior is very tolerant, right? We use priors that don't exclude networks because we know nothing and we want to have a very rich ensemble, a very expressive ensemble to begin with. So we expect rho 0 of W to have a large entropy. But of course, we have been excluding possibilities or decreasing the contribution of some of those possibilities to the ensemble according to the error that specific network configurations made on the training set. And therefore, rho m of W is going to have a smaller entropy. So there is an entropy reduction, and that's the way I like to think of learning. I like to think of learning as an entropy reduction process where I start with a very large bag of hypotheses with a very large entropy of possibilities, but little by little, I reduce the entropy of this ensemble. And this Kullback-Leibler distance, because of this minus sign, is actually measuring the amount of information gained, is minus the decrease in entropy. And this distance between the posterior and the prior increases monotonically with the size m of the training set. So this Kullback-Leibler distance will tell me, after I have seen m examples, how much information have I gained from the outside world about the task to be implemented. And therefore, it tells me by how much has the entropy of the ensemble of hypotheses that I started out with, by how much has it decreased. So let's have the following picture in mind. I started with an ensemble W, with which the big purple ensemble was controlled by rho 0 of W, which is the prior distribution. Every example psi is now predictable according to a given ensemble W and introduces a P of W given psi. So every time I see an example psi, I get a probability distribution over W given psi, which is the probability distribution induced in W given psi. So this difference in entropy, which is the entropy of the original P of W, which is rho 0 of W, minus this entropy of P of W given psi, which of course I want to average over all the possible ways in which I could have chosen the example according to, I'm sorry, this should be P tilde of psi. I should have changed that. So this entropy, which is a gain in entropy, right? Because this delta H is positive. This entropy that I start with is larger than the entropy I end with. So this entropy can be shown to be equal to the mutual information between W space, which is the space of the brain or the space of your model, and psi space, which is the space of the world that is sending you examples of the task that you are supposed to learn. And whenever you have a mutual information, you have a duality. Instead of thinking that when I see an example that affects W space, now I can think the complementary manner. If I choose an hypothesis, so I choose a network W, like each one of us is one instance of this possible ensemble of networks W. The choice of W induces a distribution in Xi space, which is not necessarily P tilde of Xi. It's not a true distribution. It's a P of Xi given W. Once I choose an hypothesis or a particular wiring of the network, I'm inducing a probability distribution in the world on the space of examples Xi. If I knew the form for this P of Xi given W, I could compute the likelihood of the data given my hypothesis. I could introduce a likelihood in space W, which is the probability of the data given W, which is the probability of seeing Xi1, Xi2, Xi given W. And if each one of them has been drawn independently from P tilde of Xi, that is going to be a product of the P of Xi mu given W multiplied from mu equals 1 to n. So any network W in my ensemble is such that I could compute the likelihood of the data given that network. But in order to do that, I would have to know what is P of Xi given W. So that's the crucial part that is missing in this. So this is what actually leads me to a derivation of the form e to the minus beta e that I propose for the survival probability. There are two possible approaches to learning. One of them is, let's compute the error on the training set. What is the error that network W makes on example mu? Sum from mu equals 1 to n. That's the learning error. I could also think of the likelihood of the data. I would say, what is the probability of the muth example? And multiply that from mu equals 1 to n. I could run an optimization algorithm that minimizes the learning error, or I could run an optimization algorithm that maximizes the likelihood of the data. So now I'm going to make a very strict requirement. I'm going to impose a very strict condition. I'm going to require that when you do that, you automatically do the other. That if your algorithm minimizes the learning error, it at the same time maximizes the likelihood of the data. Or if your algorithm maximizes the likelihood of the data, it minimizes the learning error. So if you require that, it takes about 4 pages of algebra, and I have an appendix on my slides that shows that. If you make that requirement, then suddenly the P of Xi given W acquires a form. And that form is the exponential e to the minus beta e of W given Xi. This is a probability for a fixed W. This is a probability distribution over Xi. If I integrate it over Xi, I have to get 1, and therefore I require a normalization constant, the normalization denominator, that for most error functions of interest is going to depend on beta, but not on W when I integrate over Xi. So this is why I call it C of beta. And if you're interested, I can post my slides, and then you can follow the algebra in the appendix. Okay, so now I have achieved an expression for this P of Xi given W. So now I can compute the likelihood of the data, because that was the only thing that was missing, was P of Xi given W. So the likelihood of the data is now the product of P of Xi mu given W multiplied over all the examples mu in the training set. Again, I have the products of exponentials. I get the exponential of the sum. Every time I get one of these denominators, C of beta to the m. So I get e to the C of beta to the m, e to the minus beta m is of L. So now you see very clearly why minimizing E sub L, minimizing the learning error, is going to be equivalent to maximizing the likelihood. And the two extrema would be in the same place, and for this extrema to be a minimum of the learning error and a maximum of the likelihood, I require beta to be positive. Okay, so now what I have is an expression for the probability of the data given W. So from the probability of the data given W, if I multiply by P of W and divide by the probability of the data, I get the probability of W given the data. But I have the probability of W given the data. That was rho m of W, which was 1 over Cm, rho 0 of W, e to the minus beta em of E beta M, E L of W. So are these two expressions equivalent? Yes, they are. And this is the equivalent between a Gibbs ensemble that is defined by this exponential attenuation with a well-defined free energy, a well-defined energy, which is the learning error, and a well-defined entropy, which is the Kullback-Leibler distance that is measuring the entropy reduction as you learn. And we just have to establish some equivalences. The P of W is my rho zero of W. That's the probability distribution over the ensemble that I start with. The P of W given the data is rho M of W, is the probability distribution over W space after I have seen M examples in the training set. I can get the likelihood, the probability of the data given W, which is 1 over this coefficient, this mini partition function or scaling factor, C of beta to the M, normalization factor, times e to the minus beta M, the learning error. So from this now, I have P of W given D. I can compute the evidence P of D. And then this is essentially what I get. Is the P of D is of course, the P of D given W times the P of W integrated over W. And the evidence is essentially the partition function, except for this additional normalization constant. So this normalization constant, C of beta or scaling factor, plays a very important role in the next step. We still have to compute one thing, because I've told you that the Gibbs probability distribution gives me the Bayesian, prior and posterior. I have told you how to obtain the learning error by how to compute the partition function. Take the log of the partition function, call it a free energy, compute the learning error as a derivative with respect to beta of that free energy. I told you how to compute an entropy, which is the Kullback-Leibler distance between the posterior and the prior. But I haven't yet told you how to compute the generalization error, which is always the big question for a theorist playing in this field. So how do I compute the prediction error, the generalization error? Have we acquired a good model of the brain? Has my neural network acquired a good model of the world? And then this is how we define the generalization ability. Let's consider a new point psi, which was not part of the training data, was not part of this psi1, psi-m training set. And let's compute the likelihood of this test point. What is the probability of psi given the data? Well, psi has induced a probability distribution. I know how to compute the probability of psi given W, and I know what is the probability of W given the data. So given these two factors, if I integrate over W, that will give me the probability of psi given the data. So because I know what the probability of psi given W is 1 over z of beta e to the minus beta times the error. And I know what is the probability of W given the data. It's just my rho m of W is 1 over the partition functions times rho zero of W times e to the minus beta, the sum of the errors on the training set. So notice the difference here. I'm summing the error that network W makes on example mu, sum over all examples in the training set. And here I have the error that network W makes on the new example psi. But when I multiply these two things, as this equation tells me to do, I'm just going to get the sum over m plus 1 points, where the first m are the training set, and the point m plus 1 is the new point, is the test point that I need in order to compute the generalization error. So we can now do this integral. We can write it down. And what we get is, of course, a factor of z of beta that comes out, a factor of cm that comes out. And I get this integral, dw rho zero of w e to the minus beta. And I have a sum over errors, as I said, over m plus 1 points, where the new point is the test point, and it appears as it had been added to the training set. So this is, again, a partition function. It's a partition function for m plus 1 points. And I still have the original partition function, which is the training set, is for the training set. This is for the training set plus the test point. And I have this little normalization constant C of beta. So I have been able to compute the probability of psi given the data. I'm going to use the logarithm of this likelihood, the likelihood of the test point given the data, to define the generalization error. So the generalization error, I take the logarithm of this, so I have two factors, a logarithm of Cm over Cm plus 1 over Cm, and a logarithm of C beta with a minus sign. And I'm going to define this as minus 1 over beta. Minus 1 over beta, this logarithm is a generalization error. Now, if m is very large, the difference between log of Cm plus 1 and log Cm, I can think of them as a continuous variable, so that I can define the log of Cm plus 1 minus the log of Cm as a derivative with respect to m of the log of Cm. So again, I have the log of Cm, which was my free energy, averaged over all the ways in which I could have taken a data set of size m to make it not depend on the details of the training set. I have the factor of 1 over beta, and I have an extra factor, plus 1 over beta, this minus and this minus give me a plus 1 over beta, the logarithm of the scaling factor. So now what I have is what I call a full thermodynamic theory of learning. How does this go? Construct a partition function with this exponential form for the attenuation. A derivative with respect to beta, I take the log, which is the free energy, average it over all the ways in which you have taken the training set. A derivative with respect to beta with a 1 over m gives me the learning error. A derivative with respect to m with a 1 over beta gives me the generalization error. So there is a very nice symmetry between learning error and generalization error in this formulation, but I have this pesky little factor here, 1 over beta log of C beta. It turns out that this pesky factor is very, very, very important, and it actually gives us what our intuition tells us it should be. So let me wrap this up by showing you how this works in a very, very simple case. I'm just going to do a linear transformation from the n-dimensional space into a scalar y, such that y is simply a linear combination of wxi, wixi. So it's w scalar product with x. I start with w is drawn from a row 0 of w. Every point w is coming from a normal distribution with 0 mean, and the covariance function is diagonal with a sigma, with a variance sigma w square, and the variance is very, very large. So I want to start with a very generous, with a very expressive probability distribution. Let's assume that the examples are also Gaussian. So the p tilde of x are also drawn from a normal with 0 mean, and a covariance matrix which is also diagonal with a variance sigma x squared. Let's assume a noisy environment in which y, for example, mu is a w0, which is the w's I want to learn, dotted into x mu. So this is a scalar product. This is what we call sometimes the teacher network, corrupted by noise eta mu. So now the probability of y given x is again a normal distribution, not centered at 0, but centered at the scalar product with w0 and x for a given example x, and with a variance sigma eta squared, where sigma eta is the variance of the noise. So we want to minimize the learning error, which is the target y minus w dot x, which is what the network gives us, squared, sum from mu equals 1 to m with a 1/2. And when you plug this in, you'll get a w minus w0 term, which tells you that you're going to minimize by making w equals to w0, but the error will never be 0 because we'll have this eta squared that will give you a sigma eta squared. You will be, have to deal with the variance of the noise. Well, because I started with a very expressive ensemble, I can take the limit of large sigma w and a limit of large m, and then I can actually compute the partition function analytically, and I can compute the free energy analytically in this example. And I can take the two thermodynamic derivatives that I told you about, and I can again compute them analytically to leading order 1 over m. They are corrections of order 1 over m squared, but I'm thinking of the large m limit. So what kind of terms do I have? Well, I have terms that scale like 1 over m, which is nice because m is the number of examples and n is the number of the number of weights in the network, is the dimensionality of my W space, because I have n inputs, the input vector x is n-dimensional. So I have these factors of n over m, n over m, n over m. What else do I have? I have beta appearing here and here and here. And I have sigma eta squared, which is the variance of the noise that appears here and here. So what I could do is to change a little bit the notation and think, okay, what is sigma eta squared? I can associate sigma eta squared, the variance of the noise, with an effective value of beta, with an effective temperature. So let me define beta 0 as 1/2 sigma eta squared. Let me think of beta 0 as the temperature in the world that makes examples be noisy. So that's the relationship between beta, which is a temperature-like variable in physics, and the variance of the noise. So now I can take my thermodynamic derivatives, and instead of writing sigma eta squared, I write 1/2 beta 0. And then I do a little bit of algebra, and I rewrite the thermodynamic derivatives, which now depend on n/m, as before, on beta and on beta 0, instead of having the sigma eta squared. Again, with correction, I have to order 1/n squared. And this is the result, even for this very, very simple network. And the interesting thing is that's exactly what we expect it to do. What is the role of beta in this formulation? Beta is a goodness of fitness parameter. If I let beta go to infinity, I'm back to my hard masking scenario. Beta going to infinity, which is 0 temperature, beta is an inverse temperature. Beta going to infinity means I'm back to this masking function where any error is strictly penalized. Any network that makes an error is not allowed to remain in the ensemble. On the other hand, very small beta is being very tolerant to noise. Is saying, okay, e to the minus beta EL, even if your error was very big, beta is very small, so e to the minus not such a big number, your probability of survival is still good enough. So as we increase beta, as we move to 0 temperature, as we move from soft masking to hard masking, of course the learning error decreases, right? Because we are fitting the data better and better and better and better. We are more strict about the networks that remain in the ensemble, being networks that actually fit the data precisely as beta goes to infinity. However, the generalization error is not monotonic, and it has a minimum at beta 0. So betas smaller than beta 0 means that we are being very tolerant of error. We're being so tolerant of error that we are being more benevolent than what is actually the error associated with the intrinsic fluctuations of the examples. Beta smaller than beta 0 means the examples are corrupted by noise. This noise has an amplitude, sigma, a variance, sigma eta squared, which is 1/2 beta 0, but you're estimating beta to be even smaller than beta 0. So you're allowing examples that don't fit the data, allowing networks that don't fit the data way to survive. So in this regime, the generalization error is also decreasing, but it's already larger than the learning error because we are underfitting the data. But in this regime, we are overfitting the data. The learning error gets smaller and smaller and smaller. We're fitting the data better and better and better. However, the generalization error decreases. We are losing generalization ability. Why? Because our beta is too large. We are in an overfitting regime. We are being too strict in penalizing networks because they don't feed the data well, as if the data was to be relied upon with 100% trust and reliability, which it is not because the data is noisy. So these very simple notions of overfitting and underfitting arise already in a very simple linear network with mapping n inputs into one output, but it would not arise if you hadn't have this factor, this log of pi over beta, which actually comes when you go back to the algebra for taking the derivative of the term that corresponds to, it comes from taking this derivative in the generalization error. So this little term and keeping track of the correct normalizations is crucial for devising a theory that has this competition between this beta. The generalization error increases with beta, but it also decreases because of this log of 1 over beta, and this competition between this linear growth with beta and the minus the log of beta is precisely what gives us this non-monotonic behavior of the generalization error. And moreover, it gives us the minimum at a very meaningful value of beta, which is beta 0, which is 1 over twice the sigma squared of the noise. Let me finish by mentioning another concept in which this plays an important role, which is the concept of model selection and using evidence for model selection. So let me go back to the original partition function Cm and divide by this little c to the m and define a scale partition function, such that the prediction ability, the probability of psi given the data, I can have this, I have an extra one here. So I have m plus 1 of the scaling factors associated with the numerator and m associated with the denominator. So now the generalization error can be simply the derivative with respect to m with the 1 over beta of the log of this partition function. So let's do, instead of a minimization of the generalization error, let's do a maximization of the evidence, using this partition function as the evidence, a properly scaled partition function. So we'll get the factor that we expect to get from the log of Cm, and an extra factor that comes from the log of this little z of b, if we go back to this original formulation. And so now we can ask, when is the evidence maximized? The evidence is maximized when its derivative with respect to beta is equal to 0, which happens to be at the value of beta, which is again 1 over 2 sigma eta squared. So it's again beta 0. So for this very simple case, which is a linear network with an adjustable learning temperature, with an adjustable tolerance to noise, maximizing the evidence is a good hypothesis, or is a good method for model selection. In this case, a selection of the model is a selection of the value of beta, because it coincides with the value of beta that minimizes the learning error. You can use this formalism to convince yourselves in other more complicated cases where you can still compute this free energy and compute the thermodynamic derivatives and obtain the evidence and the learning error and the generalization error. You can convince yourselves that this is not always the case, and that selecting models based on evidence, based on the probability of the data given the model, does not necessarily imply that this is the model with optimal generalization. Okay, so this is a summary of what I tried to tell you today. I tried to tell you, let's start with an ensemble view of all the possible networks, all the possible hypotheses for a fixed architecture, but depending on all the possible ways in which the weights could have been selected. And this is defined by a very versatile rho 0 of W, which we want to be expressive. So we want rho 0 of W to be broad. We end up with a much narrower posterior rho M of W. We can compute the likelihood of the data, and we can compute the evidence. And this scaling factor C of beta plays an important role in the evaluation of the prediction error, which is what allows us to decide whether the trained network has acquired a good model of the world. And you haven't interrupted me a lot at all, actually, but then we have time for questions. Thank you.
Questions?
Thank you very much. Very nice talk. Questions from the audience?
Everyone is tired.
Okay.
Hi, thanks for the talk. This idea of decreasing or increasing the temperature kind of reminded me of trading off errors in support vector machines and the like. So I was wondering if the other component of the support vector machine, namely the prior on having a low norm, whether there's sort of a different way of making sense of a limit where you essentially get a support vector machine from this statistical physics treatment. That's
an excellent comment. Thank you. This idea, this temperature idea, is just really a trade-off. It's the basic idea that you should not keep on insisting on decreasing the learning error. And is the idea behind early stopping, is the idea behind any kind of regularization in which you add terms to the cost function so that when you minimize the new cost function, which has additional terms which are regularizers, you are not going to necessarily find the W star that minimizes the learning error. So it's a very general idea, as you point out, and is this idea of overfitting by insisting on an excessive optimization, and excessive minimization of the learning error, which does not take you to architectures or to specified models or to values of the parameters that minimize the generalization error, which is what you really want. So, and the support vector machines are a special case of that, where this it's again a single layer network, but we think of it's not a single, it's a 2-layer network with a single layer of hidden units, where we use an expansive kernel in order to define a hidden layer which has higher dimension than the input, and then we do this simple 1-layer regression or 1-layer classification problem on this new expanded dimensionality representation. But the same ideas will hold. If you think that the kernel is fixed, then you don't have to learn the weights of the input to hidden. You only have to learn the weights from hidden to output, and you're back to this very simple problem that I described.
Nice. So one question. So what you just mentioned means that there is a formal connection between the bias and the variance of the estimators with this temperature formulation as well, right?
Right. So again, I want you to think of this temperature. It's a very fisted concept, but think of this temperature as how tolerant you're going to be to not fitting the data precisely, because you're doing early stopping or because you're regularizing. So you're not going to be so strictly minimizing the learning error in some sense. You're going to give up. You're going to trade off not doing the optimal minimization of the learning error for the sake of gaining generalization ability. One possibility is to understand that you shouldn't do that because your data is noisy. So it's like, I'm the oracle and I'm producing data for you, but I'm noisy. So the data that I send you is not strictly correct. So it's mislabeled or is corrupted by noise. So if you insist on fitting that data to death, that's not an optimal strategy, right?
So there are some models that have this benign overfitting kind of behavior, where sometimes you can fit the training data perfectly and still have like a descent, a descent of the risk going to zero, even in overparameterized models. Is that something that can be captured by this model that you mentioned?
So this very simple model, you would have to go to beta infinity for the learning error to go to zero. But you could imagine other models, because if you work at finite m, if m is finite, or even large but finite, I can always make a model that is expressive enough that will perfectly fit the training set, even if the training set is noisy. But again, there will be a penalty to be paid when you try to compute the generalization error for that model. So the learning error will decrease, go to zero, stay at zero, but the generalization error will decrease and then eventually increase again.
Do we have any other questions from the audience? One more?
Sure.
Thanks.
Thanks for the very interesting talk. If you're not allowed to return an ensemble of functions, but someone forces you to return just a single function, which one would you return?
Well, if you just run a risk minimization, you will return the wiring, the particular set of W's that minimize the risk, correct? That's what you do traditionally do. But if you include in the risk function that you minimize, in the loss function that you minimize, you include regularizers, you will already be playing with this trade-off between learning and generalization that I described. So So I use this ensemble idea to give you a conceptual framework for thinking about these things. Should you use this as an algorithm? That's essentially the question that you're asking me. And you could run a Monte Carlo search over this. You should not do, it's very hard to use a Monte Carlo algorithm to compute the partition function, but physicists are very good at computing free energies, which is the log of the partition function, by doing a Monte Carlo sampling of F space. So if you want to do a truly Bayesian calculation in which you keep the ensemble, you keep the prior ensemble and you keep the posterior ensemble, not just one good representative of the posterior ensemble, but keep the posterior, you will do it by using a Monte Carlo algorithm for sampling the ensemble. But again, not trying to compute the partition function, but trying to compute the log of the partition function, which is the free energy.